All right, hey guys, and welcome to another episode in this series where we're going to be designing an arithmetic logic unit. Now, given all of the things that we have here, I think we're ready to go ahead and create the arithmetic and logic unit. So, to go ahead and do that, let's create our Alu circuit. So, the two inputs of the arithmetic logic unit, of course, are still going to be A and B. So, we're still going to have to add a pin in here for the full 32 bits that we're going to be doing as our circuit. So this is still going to be input A, and this is still going to have input B. So A and B both are our inputs here. And what A and B are both going to do is that we're going to go ahead and compute a bunch of different things based upon control registers, control signals, which are going to control what sort of instructions that we're getting in. And we're going to do each one as its own sort of pin as a single bit in order to actually go ahead and hook them all up. And what that actually allows you to do is that when we have a decoder of some sort that creates instructions, we can pass in an instruction line into the decoder. So I can pass like 8 bits into the decoder, and then the decoder passes the input into the ALU. So going ahead and looking here, what we're going to have to go ahead and do is that we're going to go and start with some of the basics. So A and B both have logical operations that can be done on them alongside of arithmetic operations. Obviously, the simple arithmetic, some of the simple arithmetic operations are addition. So we're going to take the 32-bit full adder, for example, take it over here, and then we're going to go ahead and throw in the input of A, and we're going to also go ahead and throw in the input of B. Now this little unit here is now going to be producing carry out as one of the outputs, which is going to be part of the flags register. But for now, for our purposes, we don't actually care too much about what the output of the flags register is. We're just going to call it CF, which is going to be the carry flag. So once we take that, attach it over here, put this on the south side, and there we go. We now have one output from the carry flag. I'm going to go ahead and also go and add in an input pin. And this input pin is actually going to go ahead and it's going to go ahead and it's going to go ahead and it's going to basically tell us if we're doing like the subtraction. I should have made this an input pin. There we go. So now it's got two states, and then the label is going to be, this one's going to be just a pin 1. Well, I guess we should start from 0, of course. So this is going to be part of our instruction set, so P0. And what it actually is going to do is it's going to set if we're actually using subtraction mode or not. So if we are using subtraction mode, it's going to go ahead and subtract. It should not be 0, I suppose. I suppose it should be 2, because we can have not A and not B as possible inputs. So in order to do this, I'm going to keep it as P2. I'll set this to the north side, and then we're going to connect it up, down to there. The thing we can do is just toggle it as 1 or 0. Yeah, that looks fine. Okay, enable simulation. There we go. And now we have a working toggleable flag right here. So what I want to actually add in is, before this, we're going to add in our 2 more input pins. The first one here is going to be the, this one right here is going to be P0 for A, and it will be not A or not B. Technically, because we have a logic unit, and arithmetic operations and logic operations are going to be different things, we can have P0 and P2 and all of these pins have different effects necessarily. Well, aside from P1, because you will have not be as an option. So going ahead and looking at this, we're going to say that if P0 is true, so we're going to take the statement if P0 and A is going to be not, otherwise it's going to be the regular one. So we would create two lines, one of which is going to be the knotted line. So I'm going to take a gate, add a NOT gate onto this, face it down south. This is going to be the NOT side of the operation. And this looks fine. So the if P0 is enabled, then we want to go ahead and do a 32-bit NOT. So what we're actually going to do is we're going to take 32-bit NOT and we're going to actually apply it. So 32-bit NOT is one thing, right? And we can throw it up here. And then regular output is right here. So given this little cluster right here, we now know that we have 32-bit NOT and then we have a regular output. And then based upon, we're going to use an AND gate. Where is it? We're going to use an AND gate that would do two inputs. I want this to be small. So I would have an AND gate that would take in the P0 pin and then throw it there. And then we could also then take the output and we would have to pass it through. So I suppose if we wanted to have this, I should actually be able just to use a multiplexer. And the multiplexer would handle a lot of these details without necessarily having to go ahead and specify this sort of thing. So the multiplexer, here we go, would have one selecting bit and would output 32 data bits. So what the multiplexer does, disabled output floating. Disabled output, include an enable. No, we don't need an enable line. The reason we don't need an enable line is because it's got to be one or the other. I want it to be having select at the top. So what this multiplexer does is that it makes a decision based upon the P0, and we could have rolled our own, but it's going to make the circuit look really messy and it's not going to really help us. So we're going to take the 32-bit NOT as one and then this as the other. So what we're going to actually go ahead and start with is that we're going to say, what is this? Why did that form? So we're going to take one thing in here, and then we're going to take the other potential output and toss it into our muxter here. Now, what's the issue here? All right. It's got to have 32 data bits. There we go. That makes more sense. So we take that, and then we're going to connect the line here, and then take the output of A and use that on our own for other purposes. So pin 0 will change whether or not this is enabled or not. I'm wondering here if the 0 up here is going to do that or not. Let me do a quick test. I suppose we need to see what the resultant output is, so we're going to take a pin, drop it out here, and this is going to be the output, just to check. Okay. So I've connected this actually in the opposite manner, I suppose. 0 is going to be the opposite of what I want, so really easy solution. Just flip it, because it's easy enough to solve the issue. So by default, it's just going to go ahead and supply us with zeros. That is what we wanted here, and we can repeat the same exact structure for input B, except it's not going to be P0, it's going to be P1. So I'll take this, copy it, and make a second version here. This one is going to be B, and it's going to take P1 as the negate bit for B. Now, once we have that, we can go ahead and trust our outputs here and throw them into either the adder or the arithmetic side of things, or we can throw it down here into the entire sort of logic side of things. So we're going to go ahead and take the input A, toss it in here, and take B, and also toss it inside of here. This lets us now have an output that will get muxed with the other things, but we can specify that later. And then we can go ahead and have that as our result. So let's go ahead and actually create the result pin over here. It's going to be a output pin facing the west side of the east for a label for our result R. So for now, we're just going to draw the output from the arithmetic side of things. Now this is pretty nice. It's very simple. It still works as you would expect as an adder and will do whatever you need, right? So it does all the basic addition here. Now what this actually allows us to do is that we can specify subtraction, which is the 2's complement, by basically enabling the not bit here and then adding 1. What did that do? Oh, correct, because not 0 plus 1 is 0. So we can say -1, for example, which is this number, plus positive number here. Let's do like 5. Or sorry, that's not even 5, that's 8. What am I doing? 5 is going to be 4 plus 1. So 4 plus 1 is 5. 5 minus 1 is going to end up having the result here of, as you would expect, 4. If I went and did like 5 minus 3, we would get 2, and so on. If I had, for example, 5 minus 5, it becomes 0. And if I had, let's say, some arbitrary number, it will figure it out based upon the 2's complement. And that's how you can do very basic arithmetic. If something is a negative number, so let's say we have like 8 here, and we're subtracting from 3. So 3 minus 8 will result in -5. So the first bit is going to be set here, and then it's going to basically be the opposite of the result. So this would be, I believe, it would mean that we would be subtracting. It's basically the negative version, so you would have to basically go through and understand that it's not this plus 1. So take the reverse. So it's 1, 0, 0, which is going to be 4 plus 1, and that's 5. And that's negative because of the first bit being set, so that's -5 as the result. Yeah, it's kind of confusing, but it's just kind of how it works. So let's go ahead and turn off these things. And pretty much we have the ability to do A plus B, A minus B, and stuff like that as our general logical operations that we've defined, essentially. And it's a very simple and easy to understand design, basically. The other side of things now is going to go ahead and be the logic side of things. And to do logic, we're going to go ahead and reuse some of these pins to specify the different outputs. But of course, when we look at our logical operations, we're going to go ahead and take our AND, we're going to take our OR, we're going to, is AND not set up? Okay, cool. Let's just plop that down correctly by placing them here and here, and then naming it 32B, A, and D. And let's go back to the ALU. There we go, 32-bit and 32-bit OR, 32-bit XOR, and then we're going to have pretty much just a pass-through for B. So why are we doing a pass-through for B? For example, if you were to say A equals B, right, as something, we would just want to go ahead and pass B through the entire adder, straight through, and it would go ahead, or the entire arithmetic logic unit, onto the bus where it can be moved and stored as the operation, because it would be a movement operation. And it's pretty simple just to put it together with these logical signals. So we're going to go ahead and, one, make sure these are aligned, but two, we're going to take out whatever the results are here, throw them to AND, OR, and XOR, right? And then we're going to take our A line, bring it over to here, and then put it into all of these, OR, and then right into AND, OR, XOR. So now we have outputs for AND, for OR, and for XOR, which are going to contain basic data, and we're going to throw them through yet another multiplexer. We're also going to go ahead and throw this line straight across here too, which is going to be the general B line, and this is going to give out B or not B, and this allows us to do A and B, A and not B, A or B, A or not B, and then the same thing for XOR as well. And that gives us a bunch of different things that we can do. Now it's pretty simple. Once we have this to go through, now we have to add another muxer at the end to figure out what we're actually going to be using here. So P1 is pretty much reused, and it's pretty much going to be exactly as we expected it. And then we're going to use P0 and P2 to define what we want out of the logic unit. And then at the end, we'll have a third bit, and we're going to define that to be switching between, is it an arithmetic or is it a logical operation? So by doing that, we make it pretty easy. So we're going to go ahead and take a multiplexer here, and then it's going to have a data bit output of 32 data bits, and it has 2 selection bits. So it has 4 possible inputs. It doesn't need to have an enable line because it should be enabled by default. So we need to select bits, which is not too bad to add. So let's go ahead and take our muxer and then throw in every single input. So we're going to take AND is going to be the first one, OR, XOR, and then move as the bottom ones. So let's go ahead and pass it in here. And then now we have the responsibility of taking our inputs. So we're going to take P0 and P2, combine the two as the muxer output for here, because if we're doing a logical operation, P2 isn't relevant, neither is P0. So we're going to take a splitter here. We're going to have a fan out of 2 and a bit width of 2. So now we have bit 0 and 1, and then we can attach it to the muxer. We're going to go ahead and face it to the splitter, face it west, make it right-handed, and then we're going to go ahead and take in our input from P2 is bit 1, and P0 is going to be the other bit. That goes into the muxer. Muxer then puts out an input that we can go ahead and push into here. And let's delete this line just for the sake of using it. Let's say we wanted to do A and B. So if we were to do A and B, we're going to go ahead and take the inputs here. So A and B would mean that we want to see if the bits are 0. So if this is 0 and this is 0, this is going to be 0, 0, and this is going to go to the first one. Next one is that if it was 0 and 1, so I believe enabling this bit should change it to be OR. So let's take that off. So if it should be OR, oops, sorry. Oh, so this is something that I actually missed that I should have thought about. So if I'm going to be taking A for the logical unit, what I actually want to go ahead and do for the logical unit is that we want to use the source of A. We want to ignore the not side of things. So I have to go ahead and take it out here. And then we're going to go ahead and use this to tie into these two lines, and then form our own little wired connection here. And there we go. This now should do 0 and 1, and then once we enable this, it becomes an OR statement. So it just works as you would expect. So if I did an exclusive OR statement, then I would assume that the exclusive OR statement, which is going to be the third one. So the third one would be option 2. So 2 would be defined by P2 being on. So if we turn on P2, 1 and 1 results in 0, but 1 and 0 is fine, and the opposite way is fine too. So that way we can go ahead and reuse P0 and P2 to figure out what we want to do there. But now here comes the last part of making the ALU, is that we're going to actually want to go ahead and take the outputs here, and we should bring them together. And then we're going to take another multiplexer, or mux, and we're going to go ahead and put in arithmetic as the default op, and then we're going to take logic as the secondary operation. It's going to be 32 data bits, and it's going to have one selection bit, which should be on the top side. Does not need to have an enable bit. So then we're going to go ahead and take another pin as our input. So we're going to take an input pin here, toss it here. Actually, I want to set the defaults here to be facing south with no output. Data bits 1, this on the north side. Cool. And then this one's going to be P3. And P3 decides whether we're looking at the arithmetic result or if we're looking at the logical result. So based on that, just go ahead and add the result here. So now we have the very basics of an arithmetic logic unit, where we can take in a operation and we can do a bunch of different separate things that are possible now. So we can do A plus B, A minus B, not A plus B, and then we could do, I suppose we could do negative A plus B as another potential, and then we could do A plus not B, and then I believe that's the combination of things that we can do here. Anything else? These are essentially pairs. So A minus B, or in all practicality, B minus A, not A plus B and A plus not B are also possible, because then we would just have to do addition with this bit or this bit set without having the carry flag on, and then we have that as an option. Technically, we can also do a increment as one thing, so you would have B as 0 and then just put an A as A plus this bit, and then you would have a increment for whatever value you had in here. And that would work for as well. So that's basically the entire idea there. We have an output carry flag, and we have an output register, or output data here for R. So that's the arithmetic side of things. We could also do decrement, I suppose, which would be 2's complement of A. So if you had, if in register selection, it would be register A and then register A. So it would be like, so decrement would be subtraction of A and negative A, or we could figure it out essentially. Then we also have the options for A and B, A and not B, A or B, A or not B, A XOR B, A XOR not B, not B, B, and yeah, we would have not B and B as possible outputs as well. And this pretty much is the result of the arithmetic logic unit in 32 bits. Now, we should definitely have a way of dealing with stuff here for the register specifics, but I will have to go ahead and say that for this episode in the series, I think this is enough. We have a basic functioning ALU that can output results. So I think that's pretty cool. Thank you guys for watching. Please like, comment, and subscribe, and I'll see you guys later.